Okay, so and he'll now tell us all about going under the canopy, how to implement low latency BDTs with Conifer.
Thanks a lot, Tom, for the introduction. So, also to preface this talk, Conifer is a kind of friend project to HLS4ML, the talk we just heard about. So, where HLS4ML is concerned with neural nets, Conifer is for BDTs, but a lot of the conceptual design aspects are similar between the projects. So BDTs are, or decision forests, are ensembles of decision trees, where decision trees are kind of pictured in the top right, a machine learning structure that makes splits on variables to perform different tasks like classification or regression. And they were used in high-energy physics from the beginning of using machine learning in high-energy physics, and they're still relevant today. They're still used in analysis, but they're especially relevant for edge or constrained machine learning where we care about fast, lightweight, and robust methods. And I put a few references towards that. The Conifer project itself is a Python package, and similar to HLS4ML, so it's on the Python package index and can be easily installed and started to use. And then the structure of the package is kind of shown on the right to show a little bit what you can do with it. That you interface to as many of the popular decision forest training libraries that we can support. So in particular, like xgboost, scikit-learn, Onyx, yggdrasil TensorFlow, which is a solution from Google, and even TMVA. And then we read into some internal representation and write out to some different backends depending on the target deployment. And the key feature of the different backend implementations, which are kind of hand-developed and optimized, is to target high parallelism for low latency and high throughput, initially for hardware triggers for HEP experiments, but I show some other examples of where it's used. But in this talk, I'm going to talk about how some of those backend things are implemented, some of the design considerations in implementing this type of thing in FPGAs, some differences between the HLS and VHDL things, and that type of thing. So just to motivate why this thing is relevant, here are some example applications. So on the left, we have a front-end ASIC for a tracking detector, where the ASIC also has an embedded FPGA, so a really resource-constrained FPGA. So this is the readout module for a silicon pixel detector. And the team behind this work implemented a tiny model decision tree to filter based on the transverse momentum of tracks traversing the silicon detector. So you can do a kind of data reduction from the front end. And because it's so constrained, this fits within 25 nanoseconds, and that the eFPGA itself just has 500 lookup tables. But they were able to put a model in there. Then here we have an example from the CMS phase 2 level 1 trigger of improving the electron reconstruction. So we have a step where we use a BDT classifier to improve the linking between tracks and calorimeter deposits to better reconstruct electrons. And the purple curve is the version without the machine learning decision forest, and the blue is the improvement we get from adding the BDT with Conifer, which we're able to put into our FPGAs with 50 nanoseconds latency and a small resource footprint. Then on the bottom right, we heard this talk from David Riker, so I won't repeat it, but we have the tau reconstruction in Atlas running now, taking data that's using Conifer to implement a boosted decision tree to improve the tau trigger. And finally, at the top right, a kind of unconventional use of decision forests, but for image segmentation. So this example work was in the context of like a embedded medical imaging camera, which would have an FPGA in the camera device itself for assisting surgeons, for example, which was doing the task that they trained was to do segmentation of blood vessels in the images that it was taken. So on the left, you have the images. Then the next column is the truth, so the target blood vessel segmentation. And then the middle column is what you achieve with a boosted decision tree, which the team was able to put into a Kriya module with about 1,800 frames per second and 3.8 watts, which is kind of suitable for that kind of handheld device scenario. So these are some of the real-world use cases using the tools. Some of them are in R&D, but some of them are in production. And so now I'll talk about how it works, basically. So before we can talk about the implementation, I'll just introduce how decision trees actually work, not in terms of training them, how we decide which splits they should perform, but how the inference works. So we always have a structure like this, a tree, top-down tree structure, where we start at the top, the root node, and we have some data. So in this case, we have 8 variables, just for a dummy example, and each node looks at just one variable and simply compares the value of that variable to a threshold, which is determined at the model training time. So for inference time, for making new predictions, it's fixed. And depending on the outcome of that comparison, we either go left or right. So in this case, we're asking if that 4th variable is less than or equal to 7. And if I plug in some dummy data here, we can kind of go through the example. So in this case, in the example, the value is 3, so we're going to go left. And then we'll look at the next variable, which is the 7th in this case. And the learned splitting on that node is to compare it against the value 2. And then we can compare it against the real value that we have for this prediction and go left again, right again in this case. And then we reach a leaf node. So that's a node that doesn't make a split. That's the end of the decision path. And here the values that are stored at the leaf nodes are basically related to the proportion of the different classes that were present after doing those splits in the training data. So this is somehow then the probability that this data belongs to one class or the other class in the machine learning problem. But all of the values that have gone into this model were learned in the training step, and for making new predictions, they're kind of statically defined, and we can profit from that for the FPGA implementation. But that's the general procedure for a decision tree. We start at the top, we make these comparisons until we reach a leaf. Then a decision forest or a boosted decision tree or a random forest, similar versions of the same thing, is basically an ensemble of these individual decision trees. So you have many of them, typically hundreds, all trained independently or additively from the previous tree. But at the inference time, they're all independent, and that's something we can profit from for making fast predictions with massive parallelization. So we go through a procedure of making the predictions for each tree independently and then summing up their results to get the final probabilities. So the way this was implemented in Conifer, as branching implementations can be quite difficult to implement in logic, especially with low latency, was to invert the problem. So instead of starting at the top and reaching the bottom, we instead ask for every node at the same time, does the decision path go through this node? So we can kind of show an example. If we start at the leaves, then the decision path will go through this particular node if it went through this node, and depending on the outcome of the comparison that was done at that node. And then basically it's the same procedure for the node above. That node, the decision path went through it if the root node was active, and the comparison at that root node went left. And this way we can basically make a kind of logical implementation of the branching instead of actually doing branching. And the decision path always goes through the root node, so we can kind of assume that one. So in the Conifer implementation, which is true for both the HLS and the VHDL, we basically evaluate that kind of logical expression for all of the nodes in parallel. So it's kind of brute force. We do a lot of computations that are kind of wasted because the decision path can only go through one path, and we'll evaluate every node. But this way we can massively pipeline it, massively parallelize it. So we parallelize by going over all of the nodes simultaneously. We pipeline so that we can start a new prediction on every clock cycle by pipelining the logic, basically. It's a string of Boolean operations. So then for each leaf node, we have a Boolean expression, which is going to be evaluated to true if the path went through the node, and otherwise it's false. And then we can use the bits from each leaf node to look up into a small table with the pre-computed probability values, and that's the tree scores. So this is kind of how it looks this is then the scheduling view from the HLS synthesis, which I haven't actually introduced yet, but this kind of shows that it worked as intended. So the x-axis is time, and the y-axis is different operations. And the block at the top that's highlighted in the orange box is all of the comparisons. So we just evaluate every possible comparison for every node at the beginning. And then all of the other operations are this string of Boolean logic to compute the decision path. But unlike the original phrasing of the branching problem, there's no data dependency in the computation that we do here. We just always do all of it. And then we kind of aggregate the result at the end to get our tree score. So that's the brute force low latency implementation. I guess I can go back one. The x-axis was time measured in clock cycles, and you see it's 3 clock cycles to do the inference of one tree. And then this is the scheduling view of a forest. So each green bar is then one decision tree. And since each decision tree can have a different structure, you can see that different trees can have a slightly different latency because they'll be scheduled independently. But this one's quite simple to understand. We execute the inference of all of the trees in parallel, and then we sum up the results in a kind of adder tree. So for this dummy model with 20 trees and a depth of, I think, 3 or 4, 5, we're able to achieve a latency of 7 clock cycles in the FPGA at some 100 to 500 megahertz kind of clock frequency. And it's all pipeline, so you have an initiation interval of 1. So I used those scheduling views to get a view at how the implementation works, but that view would also hold true for this VHDL implementation that we have, which is kind of handwritten, handcrafted VHDL of the same idea of doing the brute force parallelization. So these plots kind of show the comparison between the HLS and HDL, and also kind of motivate why the VHDL implementation was written. So just to go through the key, you have the HLS-C synthesis, which is taking the C++ code and producing RTL. And then we have logic synthesis, which is taking the RTL and producing a netlist. And that we can do for the HLS-generated RTL and for the handwritten RTL. And after the C synthesis step, we get some estimates from the HLS tool about what the resources will be. And you can see from these plots that they're basically pretty bad. But after the logic synthesis, the HLS results are actually quite compatible with the VHDL results in terms of the resource usage. So that's by seeing that the orange circles and the blue pluses are kind of overlapping quite nicely. So the implementations are quite equivalent until the thing kind of breaks down. So what you don't see is there are some kind of steps in that plot, basically. So for models above a certain size, the HLS tool kind of just gets stuck and can't achieve as good results anymore. Whereas the HDL handwritten implementation scales to much larger models without deviating from the kind of expected scalings, which is motivating why that was written. There is a kind of caveat that these results were made with a much older HLS, and the tool supports the most recent Vitis HLS as well, and the performance is incrementally better with the newer HLS releases too. The other effect we see is on the bottom row, looking at the latency. So the VHDL implementation is also fully pipelined, but then it's kind of hand pipelined. So I had to place the clock cycles in the code, whereas with HLS, the scheduling is done by the compiler, as we kind of saw in those waveform views previously. So the HDL implementation is kind of conservatively pipelined, meaning that sometimes the HLS version can achieve lower latency, which is relevant for the kind of trigger applications. So it probably means that the HDL version could be tuned to get the same low latency, but it's a kind of manual process. And then there were some certain dependencies or scalings in these plots that are kind of intuitive, that the resources increase linearly with the number of trees, exponentially with the depth of the trees, since the number of nodes goes exponentially with the depth. And the latency increases logarithmically with the number of trees and linearly with the depth. So that was the kind of the two back ends of the Conifer project that I described, which is for static BDT evaluation. So that's where we take one trained model with its thresholds and scores and really implement that as one net list. Then you have to go through one place and route for that specific model and get one bit file. And if you'd like to change your model later, you have to redo that process. So the next section, the final section, is to talk about a more dynamic and reconfigurable implementation that has been dubbed the forest processing unit. The idea being that we'd like to have a flexible architecture for doing decision forest inference that we can load new models onto later. Similar to the kind of DPU idea for neural networks. So the first idea is to represent the decision forest or BDT as data and how to derive an architecture that can do inference on that data and load new data for a new model over some bus. So the base unit is what we've called a tree engine, where the data just goes into some memory, and then there's some simple logic for doing the tree traversal, which is now kind of going back to the naive tree traversal, starting at the root and iterating until we reach the end. And there's a kind of neat flat representation of trees that's used in scikit-learn and that we've adopted for this FPU as well. So I won't go through the code for time basically, but it's there kind of for reference to show how you can make an architecture like this from HLS code, which is kind of neat, but it's starting at a root, doing the comparison, and then going left or right by reading the next value from the memory until reaching a leaf. So that's the tree engine unit. And now the iteration logic, compared to what we were doing in the previous examples, has what is called a loop carried dependency in the jargon, and also a data-dependent latency. So in our HLS reports, we get an unknown latency for how long it takes to do an inference, because it depends on the structure of the data itself. But we have this then interval of 3 for the loop, because we have to do a read, a compute, and then another read. Then the whole forest processing unit itself is putting together as many of these tree engines as we can fit into one device and to get, while still achieving time enclosure. And the aggregation is the same, that we use each of these tree engines to do the inference of one tree, and then we sum up the results to get the final model prediction. And then the number of tree engines will constrain the eventual largest size of model that we can fit. But since the model itself is now stored in some memories that are connected to some bus, we can load new models later. And then I won't talk about this, but basically it makes use of having some static arrays for the nodes, and that's basically all that was needed to achieve the reusability part. And then this is kind of how it looks in some floor plans, so it's just to say that it works basically. So for some Alveo cards, we could fit 200 of these tree engines, and in a PINC-C2 we could fit 100, where it's also a bit easier to see the use of the blockrams in the columns for all of the tree engine memories, and then the logic that sits nearby to do the actual inference. And then we use the kind of easy to access through HLS AXI buses for loading data. And the Conifer tool then also provides a Python interface to loading models and doing inference through the PINC framework. And the whole design is written with HLS. So here there is no HLS versus VHDL comparison, apart from to say that I didn't have time to write the thing in VHDL. So here the use of HLS was that it's a kind of productivity tool. It enables achieving quite complicated designs without too much effort, actually. So that brings me to the conclusions. Conifer, as I've described it, is a tool for mapping decision forests onto FPGA firmware in a couple of different ways. It's easily accessible, so you can pip install it. And then in this talk, I discussed at the beginning some of the applications, and then throughout the rest of the talk, the various implementations from the static implementation with HLS and HDL, and lately this forest processing unit reconfigurable design. Thank you.
Thanks, very interesting talk. Any questions? David at the back.
Thanks for the really interesting talk. I had a question about the comparison between the sort of brute force traversal of the tree versus the standard one where you start with the root node. Have you measured the power usage difference between the two? Because one would naively expect the brute force to have a higher power usage.
I haven't measured the power usage, actually. No, not the power difference. I didn't say it, but the latency of the flexible design is longer than the brute force design by virtue of that loop carried dependency. It still can achieve the kind of sub 100 nanoseconds latency, but I haven't compared the power between them, no.
Hello. Hi. You nicely described the tree implementation. Does your design change if you change boosting methods? It seems like you mentioned xgboost versus, I'm guessing, AdaBoost and other things.
Yeah. Basically, no, because you always have the ensemble of trees where the iteration of the decision tree is always the same between the different methods, basically. And they're all independent, so you can parallelize in the same way. Some methods differ just by the way the aggregation is done. So rather than summing them up, you might take the median prediction, for example. But yeah, that's a kind of smaller difference than just the tree part.
Okay, there are no other questions. Let's thank the speaker again.
Thanks.